Hey guys, welcome back. Today we'll be looking at hashing. We are still on the introduction to cryptography remote triacme. We've touched the symmetric encryption and the asymmetric encryption. Now moving on to hashing. A cryptographic hash function is an algorithm that takes data of arbitrary size as its input and returns a fixed size value called the message digest or the checksum as its output. For example, SHA-256 sum calculates the SHA-256. SHA means Secure Hash Algorithm Message Digest, and SHA-256, as the name indicates, returns a checksum of size 256 bytes, which is the same as 32, sorry, 256 bits, which is the same as 32 bytes. This checksum is usually written using hexadecimal digits. Knowing that the hexadecimal digit represents 4 bits, the 256-bit checksum can be represented as 64 hexadecimal digits. We know that 8 bits equals to 1 byte. So if we're having 4 bits, that will give us how many hexadecimal digits from 256 bits? That's 64. In the terminal output below, okay, let me start my attack box. By the time we get there, we'll be able to use the machine. I'm going to minimize this. In the terminal output below, we calculate the SHA-256 hash values for two files of varying sizes: 4 bytes, 275 MB, and 5.2 gigabytes. Using SHA-256 sum to calculate the message digest for each of the three files, we are going to get three completely different values that appear random. From here, we can see that we use the SHA-256 sum for each of them, and we have the one for the 4 bytes, the 275 MB, and the 5.2 gig. The SHA-256 form, they are all different. Now, it is worth stressing that the length of the resulting message digest or checksum is the same, no matter how small or big the file is. In particular, the 4-byte file, that is the abc.txt, and the 5.2 gigabyte file resulted in message digest of equal length independent of the file size, as you can see here. We have the equal length. But why would we need such a function? There are many uses in particular. One, storing passwords, and two, detecting modifications. Storing passwords. Now, instead of storing passwords in plain text, a hash of the password is stored. Consequently, if a data breach occurs, the attacker will get a list of password hashes instead of the original password. In practice, passwords are also salted as discussed in later task. 2. Detecting modifications. Any minor modification to the original file would lead to a drastic change in the hash value, that is the checksum. What this means is that if I were to write I am female and I get the hash value for that, if I end up writing, if it get modified and turns out to be I am male, the checksum is going to be different. The hash value is going to be different. So once there is any little modification, it gets detected. In the following terminal output, we have two files, text1.txt and text2.txt. As we can see, they are almost identical, considering the letters capital letter T triacme and small letter t triacme. We can see that the X digits are different. For the capital letter T, we have 54, and for the small letter t, we have the 74. Now, even though we have flipped only a single bit, which is the t, it is evident that the SHA-256 checksums are entirely different, as you can see here, entirely different from this. Consequently, if we use a secure hash function algorithm, we can easily confirm whether any modifications have taken place. This can help protect against both intentional tampering and file transfer errors. Some of the hashing algorithms in use and still considered secure are SHA-224, SHA-256, SHA-384, SHA-512, and the RIPE MD160. Some older hash functions, such as the MD5, that is Message Digest 5, and SHA-1, are cryptographically broken. By broken, we mean that it is possible to generate a different file with the same checksum as a given file. This means that we can create a hash collision. In other words, an attacker can create a new message with a given checksum, and detecting file or message tampering would be possible. What this means is that two different files can have the same hash output. That's what is known as hash collision. They have different contents, different things, but the checksum is going to be the same. So now this can be very difficult to detect when there's message tampering or if it has been altered. HMAC, hash-based message authentication code. This is a message authentication code that uses a cryptographic key in addition to a hash function. According to the RFC 2104, HMAC needs 1. Secret key, 2. Inner pad, 3. Outer pad. Now, the inner pad and the outer pad, they are constant strings and they are repeated quite a number of times. The inner part uses 0 times 36 repeated in capital letter B times, and the value of B depends on the chosen hash function, and the same applies to the outer part. To calculate the HMAC, we follow the steps below. 1. We are going to append zeros to the key to make it of length capital letter B. That means it must match the length of the iPad. 2. Using bitwise exclusive OR, represented by this signal, we calculate the key iPad. 3. We are now going to append the message output from step 2 to the key iPad. That's what we have here. Now, 4. We apply the hash function to the resulting streams of bytes. So the key iPad that we got will be added to the message. Then we subject them to the hash function. Now 5, using XOR, we calculated the OPAD. Once we calculate the OPAD, we are going to append the hash output from this hash function step to the OPAD. Now we are going to apply the hash function again to get our HMAC. Now to calculate the HMAC on a line, I hope you understand what I just did. What I explained there is we have a secret key, the inner pad and the outer pad. Once we've been able to get the inner pad rather, we are going to append the message to it. Once we append the message to the inner pad, we subject it to the hash function. Now we know we have an outer pad too. Now we are going to append the outer pad that has been don't forget that the key has been calculated with the outer pad here. It's the same as the inner pad. The hash output that we get after using the hash function on the message and the iPad will be appended to the O pad. Now that we have the outer pad, we subject them to the hash function again. Then we have our HMAC, which is the hash-based message authentication code. Now, the figure above represents the steps expressed in this formula here. To calculate the HMAC on a Linux system, you can use any of the available tools, such as the HMAC 256 or the SHA-224 HMAC, SHA-256 HMAC, SHA-384 HMAC, and the SHA-512 HMAC, where the secret key is added after the option key. Don't forget that we have 3 things: the secret key, the inner pad, and the outer pad, which are constant strings. Now, below, we show an example of calculating the HMAC using the HMAC 256 and SHA-256 HMAC with 2 different keys. We can see here we have HMAC 256 and the key. We have the HMAC 256 and another key. Now we try using the SHA-256 HMAC plus the key. You can see that either we use SHA-256 HMAC or HMAC 256, we are going to have the same output for the same file using the same key. On the attack box, you can find the directory for this class located as tax05. Alternatively, you can use the tax file from tax2 to work on your own machine. So I'm going to show split view now. Once I show split view, we are going to take on what? could not be found. As in, as how? Mm, okay, let's refresh the page. Failed to connect to server. We are going to terminate the machine and try again. Mm. So I'm going to have to wait for the machine to load. Just going to take a few seconds. Okay, we are good. We're going to start the terminal. We are going to navigate to this directory. CD root owns cryptography intro class of 5. Okay, we are there. So we are going to list the contents. Okay, we can see that we have the order.json. What is the SHA-256 checksum of the file? Order.json. So we're going to do SHA-256 sum order.json. So this is it. We're going to copy it. We're going to submit. Correct. Open the file order.json and change the amount from 1000 to 9000. What is the new SHA-256 section? You can use nano or vi. Let's use nano. Order dot json. We are going to change 1000 to 9000. Okay, sorry. I remember the last time I used nano. Got that vehicle. Mm-hmm. We're now going to check the SHA-256. Let me cut. Let me see if other the changes have been made. Okay, yes, it has been made. Now we're going to check the checksum. Yeah, SHA-256. Okay, you can see that the output is now very different from what we had, just because we changed one figure. We changed 1 to 9. Our output is very different. Using SHA-256 and the key, what is the HMAC of order.txt? So that's going to be Control L, SHA-256 HMAC, right? For what? For order.txt, order.txt. Then we have the key, dash key. What's the key? Okay. 3 RF DF. That's capital letter F. Z 82. Enter. Command not found. Why are you disconnecting now? Okay. If it doesn't have that command, we are going to try using HMAC 256. These are going to get the same results anyways. HMAC 256, the key, and the file. I think I'm supposed to put the command key there, right? Okay, no. Okay, so we have the no, what's wrong with the attack box today? And we submit. So with this, we've come to the end of the hashing room, the hashing task for this room. We looked at HMAC. We looked at SHA-256 and how to use it to get the checksum. And we've done some exercises, like 3 examples, just to be able to check the output, or how to check the integrity. And we've also been able to edit the content of the file and see how the checksum differs once there's a just one figure alteration. Thank you very much for listening. Bye.